Hello, welcome back to our course on Advanced Quantum Mechanics. This is lecture 12. Let me remind you of where we left off last time. We were considering changes of bases. And to that purpose, we introduced linear operators that we called U or U hat. I think there should be a hat on them to indicate that they're operators. Linear operators U hat, which map the basis vectors of one Hilbert basis, let's call it Bn, into the basis vectors of another Hilbert basis, let's call them Cn. Okay, so if you apply the change of basis operator, the change of basis map, U hat on Bn, you get the Cn by definition. Now, something that we had not discussed last time was that these are not just any bases, these are Hilbert bases. And that implies in particular that they are consisting of orthonormal vectors. So the Bn are orthonormal. So that is this condition here, that they are orthonormal. And we also have the fact that the Cn's are orthonormal. That's that condition here. Now, if we take an orthonormal basis and apply an arbitrary linear map to them, then of course the image vectors don't have any reason to be orthogonal. They could be just wildly mixed through another, and their length could be changed, the relative angles could be changed, all of that. But no, we don't want any of that. We want that the image under the action of U is consisting of orthonormal vectors as well. What does this mean for the linear map U? Well, let's just calculate that. Let's just calculate the inner product of the Cn and the Cm. For that purpose, we write down the ingredients here. We have that Cn is U hat Bn, Cm is U hat Bm, and therefore if we turn this ket here, for example, into a bra, because we actually need to take the inner product of two of those C vectors, if we turn that into a bra by applying Hermitian conjugation to this equation here, then what do we obtain? The Hermitian conjugate of the ket vector Cm is of course the bra vector Cm. And the Hermitian conjugate of this is, if we are careful, we just write down U hat Bm, the whole thing in brackets, and then Hermitian conjugation. What is it when we work it out? Well, it is the Bm vector as a bra vector now, and then the U hat becomes U hat dagger. How do we see that? Well, remember, we have under Hermitian conjugation that for any matrices A and B, or linear maps, or vectors, for any A and B, we have that the dagger of the product of both of them is the B dagger, A dagger. So that's true not just for n by n matrices or infinite by infinite matrices, but also if one of them is a vector, as we have the case here. All right, so now we have the ingredients to check the orthogonality condition. I mean, to check what the orthogonality condition implies for the linear map U. So we just take now the inner product between the Cm on the left and the Cn on the right, or the other way around. So we calculate the inner product of a Cn and the Cm. What is it? Well, the bra of a Cn is Bn U hat dagger. We just calculated that here. And the ket of the image of a Bm gives us a Cm under the action of U hat. So Cm is U hat Bm. And now we remember that the Bn and the Bm are a Hilbert basis. They are an orthonormal basis in the Hilbert space. And we now know that these matrix elements here have to be delta Nm. But which operator has as its matrix elements delta Nm in a Hilbert basis? only the identity operator, because this is literally the identity matrix, right? It is 1 for n equal m and 0 otherwise. So what we have here is that this is the identity operator because the whole thing is the identity matrix. All right, so we have that U dagger U has to be the identity matrix in order for the CM to be orthonormal if the BNs start out orthonormal. So the fact that we require that the map U hat conserves the inner product between the basis vectors, namely the length and orthogonality, translates into the condition that this linear map U hat must obey the equation U hat dagger U hat equal to the identity map. If we multiply this equation from the right with U hat inverse, we obtain that the condition on U hat is that U hat dagger is U hat inverse. This leads us to a definition. All operators on a Hilbert space that obey this condition are called unitary operators. You know, of course, a unitary operator right away, like the identity. Identity is a unitary operator, right? Because it is its own Hermitian conjugate, it's also its inverse, so yeah, that's automatically true. But of course, any change of bases will do that preserves the orthogonality and norm, that is the length of the vectors. Intuitively, unitary operators can be viewed as complex rotations. This is not a technical term, complex rotations. It is just something I'm saying to give you some intuition. So why are they complexified rotations, the unitaries? Well, let me remind you of what a rotation is. A rotation in R2, or a rotation in R3, or a rotation in any real n-dimensional space is defined to be a map which preserves angles and lengths, which preserves in particular the overlap between any two vectors, because if you have two vectors, then the overlap, so the bracket of two vectors, the scalar product of two vectors is of course the length of the first times the length of the second times the cosine of the angle between them. Rotations preserve all of that. And it turns out that unitaries do the same thing, just in a complex vector space, namely in a Hilbert space. So to see that, let us look, for example, at two vectors in the Hilbert space, phi and psi, and let us look at their inner product. Now, their inner product is this. Now, let us map the two vectors under a unitary transformation. So let's say we take phi, apply the unitary transformation on it, and we get phi tilde. Similarly, under the unitary transformation, our psi goes into a vector that we may call psi tilde. Now let's see, what's the inner product between psi tilde and phi tilde? And how does it compare to the original inner product before they were mapped under a unitary? Well, after the unitary acts, we calculate now the inner product between the phi tilde and the psi tilde. And what is it? Well, phi tilde is u hat phi, but that's a ket vector. If we want to know the Bra vector, we have to take the Hermitian conjugate of this. But the Hermitian conjugate is going to be phi u hat dagger. Remember from above that this picks up a dagger here. And the psi tilde is u hat psi, so it's all of this. And now we notice, aha, we have that u hat dagger u hat is the identity, and that means that we just get back the original scalar product. So in fact, the unitaries are those maps that preserve the inner product on complex Hilbert spaces. They preserve the lengths and the angles. So now that we are proficient at changing bases what basis should we choose? In practice, it turns out that often it is useful to choose what is called the eigenbasis of an observable. So in practice, it is often useful to choose a Hilbert basis. Let me just write basis. A basis of eigenvectors of some observable, one or several simultaneously. Let's call it f hat, for example. Let's just write e.g. f hat. So that basis could then be a basis of vectors that we may call fn. And then the n run through some index set I. So this would be an index set such as the index set could be, for example, 0, 1, 2, and so on. But the index set could also be, I don't know, all integers, for example, positive and negative integers. But the index set could also be continuous. It could be the interval from, just a sec, could be the interval from, I don't know, 3 to 7. Or it could also be the real numbers. It could even be a mixture of integers and continuous intervals. And we would have that f hat, our operator, applied to any one of those fn vectors would be fn, fn. Now that's a lot of fn's in here. Let me just clarify that. This is, of course, eigenvector. This would be an eigenvalue, so this is a number. So this thing better be in the Hilbert space, but maybe not. And this would be an eigenvalue. And then that's, of course, the operator. I'm writing this out because we're using f for 3 very different things here. And it needs to be taken into account from the context, what is meant. So that, you know, the f hat is the operator, and then if it's a cat, it's a vector, and then if it just stands for fn just on its own, then it's a number. Now, how do we even know that for a given observable f hat, such a basis even exists? How do we know if for a given f hat, such a basis exists? See, it's all good and fine to say we just choose an eigenbasis, a basis of eigenvectors of our observable, but how do we know it always exists? Well, it doesn't always exist. It turns out nope. It doesn't always exist. That is to say, there are f hat for which it's not true, they don't have an eigenbasis, and yet they do count as observables. It's a very subtle point, but very important point. But often we know it exists, that is to say such an eigenbasis exists, because of the spectral theorem. Now let me write that on a separate line. Because of the spectral theorem for self-adjoined operators. Now, so that's going to be our mission now, finding out what is the business with the spectral theorem, when does it apply, when does it not, and if it does, what does it mean? You see, this has super important measurement theoretic consequences. This is very subtle stuff, and I will always point out when it becomes subtle, and by subtle I mean new features that are only existing because the Hilbert space is infinite dimensional. So they could not be seen in linear algebra. And these cool features are necessary to describe the fancy things that quantum theory does when it comes to making predictions. For example, the uncertainty principles and limitations to the ability to know things in nature go back to uncertainty principles and related mathematical principles, and they ultimately trace back to this question here, namely, when does the spectral theorem apply? And when it does apply, what does it mean? Now, in order to do this, in order to get to the spectral theorem, we will need to clarify first a few definitions. What do we mean by spectral? What is this about? What is the spectrum? What is the spectrum of an operator? And then, what is self-adjointness? What exactly do we mean by self-adjointness of an operator? So what we will do now is we will first study self-adjointness, and then second, we will study the spectrum of operators, and after that we are ready for the spectral theorem. So we begin with self-adjointness. Here we go. Definition. An operator F is called self-adjoined if it is the same as its adjoint. That sounds easy enough, but believe me, it's not trivial. So an operator, let's call it F hat, is called self-adjoined if F hat is equal to F hat dagger, its Hermitian conjugate, and so they act the same way on vectors, right? And if, and that's the second condition, if the domain of F hat is equal to the domain of F hat dagger. That seems like it's a subtle, it seems like it's a, tricky thing. And it is, we have to be very careful. It's very important, but easy to overlook. Just because two maps act in the same way on vectors, F hat does the same as F hat dagger, doesn't mean that the two maps are the same. Because it could be that one map is allowed to act on more vectors than the other. Remember that this can happen when you have infinite dimensional Hilbert spaces, namely that vectors cannot act on all of the Hilbert space. They can only act on a subset of the Hilbert space vectors. Namely, on that subset, in particular, they can at most act on those vectors which they map into the Hilbert space. if they would map a vector out of the Hilbert space, then that vector cannot be in its domain. So we have to check not only that f hat and f hat dagger act the same way on vectors that both can act on, but also for self-adjointness, we have to check that both are allowed to act on the same set. And that's non-trivial, coming from the definition of what f hat dagger is. So what is the domain of the adjoint operator? What is the domain of the adjoint operator? How does it act? Let's go back to the intuition and then turn it into a proper definition. So the intuition is, of course, this. Intuition is this. Remember that when we write such a matrix element, phi q hat psi, where q hat is an absolutely arbitrary operator, So it could be an observable, it may not be, it could be unitary, could be self-adjoint, could be anything operator. Then what we mean by that is that you first apply q hat onto psi, and that gives you a vector, and then you take the inner product with phi, right? This is what we always mean when we write down such a thing. We bracket it in this way. Just because, as always in math, we work from right to left. We start with psi, then apply this operator on it, and then we apply that vector on the resulting vector here. So that's that. Now, we want to define the adjoint operator for our operator q hat, so that intuitively, instead of having q hat act to the right, we should be able to have q hat dagger act to the left on the phi, and the scalar product should still be the same, right? So the q hat, the adjoint of q, we define to be that operator which accomplishes that. So instead of acting with q to the right, q hat is defined to act to the left such that the same inner product comes out. So what we want is this. We define a q hat for q such that phi q hat psi, as always bracketed in this way, is equal to, let's call it phi psi with phi equal to q hat dagger capital Phi. Okay, so what did we just write down? We said that when q hat acts to the right on psi, then we should alternatively be able to have an operator that acts on the phi instead, and then we get the same inner product. So instead of calculating q hat acting on psi and then the inner product with phi, we should be able to calculate the inner product of psi with a vector phi, where phi is obtained by acting with the adjoint operator on phi, on this phi here. So here's the proper definition then. So basically, all I want to say is that the adjoint, if an operator acts to the right, its adjoint accomplishes the same job by acting to the left. Here's the proper definition. See, ordinarily, this would all be very simple. In linear algebra, we know what the answer is to this. In linear algebra, you have to take the Hermitian conjugate of your matrix. You have to transpose your matrix and take complex conjugate of its coefficients, and that's it. This is how you get the adjoint matrix. But not in infinite dimensions. There is an issue of domain, namely on what vectors the adjoint operator can act. So the definition is this: assume given some operator Q hat with domain d Q hat, which is a subset in the Hilbert space, and we assume the subset to be dense in H. If you remember, I think I mentioned this once or twice before, a subset of the Hilbert space is called dense if no vector in the Hilbert space is orthogonal to the subset. So we are not missing out on any actual dimensions in the Hilbert space. It's just a matter of limit taking. Okay, so let's assume we are starting with some operator and its given domain. Then the definition is then the domain of the adjoint operator of Q hat dagger, that's the domain of the adjoint operator, is the set of all those Hilbert space vectors for which there exists a vector phi in the Hilbert space, no, one of these, just color that here, one of these, for which there exists a vector phi so that phi psi is equal to phi Q hat psi for all psi in the domain of our operator Q hat. This is just writing out in compact mathematical language what we discussed above here under intuition for what we want. This is all a little bit tedious, but it's just a measure of caution because our Hilbert spaces are infinite dimensional. Right, so now we have defined the domain of Q hat, namely consisting of all those vectors for which there exists a vector such that we can throw the action on the left, and then we define that Q hat dagger acting on phi is this little phi vector, and that's for all phi in the domain that we just defined of Q hat dagger. All right. Okay. Now, what self-adjointness means, so we just defined what the adjoint is of an operator. It's a refined version of Hermitian conjugation, right? In linear algebra, there would be no difference between taking an adjoint and taking the Hermitian conjugation of an operator, of a matrix. But in infinite dimensional Hilbert spaces and nature forces us to work with them, they're not the same. They're the same up to issues of domain. So it's still true that if you have a matrix, an infinite by infinite matrix, and you calculate the adjoint, it will be obtained by transposition and complex conjugation of the matrix elements. But the domain on which the adjoint acts may be different from the domain on which the original operator acts. You see, domain issues never arise in finite dimensional linear algebra because all lengths are finite of the vectors when you apply a linear map on them. Okay, so now what does self-adjointness mean? Now, definition, an operator f hat is called self-adjoin, self-adjoin, if two conditions are met. A, we must have that f hat acting on psi is equal to f hat dagger acting on psi for all psi in the domain of f hat, and we need B, that the domain of f hat is equal to the domain of f hat dagger. And as we will see later, we'll see later that there are important cases of f hat observables for which A holds but not B. Let me give it away a simple example of that. Example, here we go. Example, the momentum operator p hat of a particle in a box. Momentum operator of a particle in a box obeys. It obeys formally that p hat dagger is equal to p hat, but it's not self-adjoint, and the spectral theorem doesn't apply. You may wonder, okay, is that just some sort of subtle point that is only of interest to pure mathematicians? No, it has physical consequences. It means that the uncertainty in the momentum of a particle in the box cannot be made smaller than a certain finite amount, which is h bar divided by L. So this implies but we just spell it out so that you have it in the notes, but dp hat is not equal to dp hat dagger. So the domain of the momentum operator of the particle in the box is not the domain of its adjoint. And this implies, for example, this feature that delta p, the uncertainty in the momentum, as we will see later on, is always equal to, larger equal to, and if I remember correctly, it was h bar divided by L. So you can't make the momentum any sharper than that. And where does this come up? Well, for example, in a case that I mentioned previously in the lecture, namely for microscopy and for astronomy. There is a limit to how sharp an image can be made using a telescope or a microscope. And that has to do with the opening size of the lens. That opening size of the lens corresponds to the size of a box through which the photon must come in. And measuring the transversal momentum of the photon is measuring the angle from which the light came. So having a fundamental minimum uncertainty in momentum for a particle in a box translates into having a fundamental minimum uncertainty in the angle resolution of imaging when you use a lens. And that goes back to that subtle difference between an operator that is self-adjoined and an operator that looks self-adjoined but isn't. And let me give you the definition here. So an operator f hat is called self-adjoined if A and B hold, and definition, sorry, I think it's too early for this definition. It would be confusing to squeeze that into this here. Okay, so we went after the spectral theorem for self-adjoined operators because it tells us when we can find an eigenbasis for an observable. Now let's see what went into it. The spectral theorem for self-adjoined operators requires the definition of self-adjoined. That's what we just discussed. So f hat must be acting the same way as f hat dagger, but f hat and f hat dagger also must have the same domain. We will later see concretely where this matters. And then secondly, in order to be able to cover the spectral theorem, we need to discuss spectra. What is the spectrum of an operator? So in order to do this, we first need to reconsider what is an eigenvalue. What is a spectrum? What is an eigenvalue? So what is the spectrum spec of Q hat of an operator Q hat? Well, let's start with the definition. Assume Q hat is an arbitrary operator, is an arbitrary operator on our Hilbert space H, on H, on some domain in H. Then psi, which is some vector in the domain of Q hat, yeah, I should actually write it like this, it lives on its own domain, d Q hat, which is a subset of the Hilbert space. Then a vector on which our operator Q hat can act is called an eigenvector. You may think, oh, this is boring. I've seen all of that in linear algebra, but just wait a moment. An eigenvector of Q hat with eigenvalue lambda. Lambda, some complex number. Remember, Q hat is any operator, and so it could have real or complex eigenvalues. If, so psi is an eigenvector to Q hat with eigenvalue lambda if, well, Q hat acting on psi is lambda psi. Okay, let's call this equation star because we'll have to come back to it in a moment. all of this is just like in linear algebra so far, right? Eigenvector, eigenvalue, easy. But remember, we already discussed that in quantum theory, we can't get around the fact that sometimes we have eigenvectors that are not really in the Hilbert space, that are not normalizable. How can we work with this? They are outside the framework in which we work. We work with Hilbert spaces. If the supposed eigenvectors are not in the Hilbert space, how can we possibly be mathematically rigorous? Now, here's the trick. First of all, we start with the eigenvalues. It is in fact possible to rewrite such a condition, an eigenvector condition, eigenvector-eigenvalue condition, without referring to the existence of an eigenvector. It's a very clever trick that mathematicians came up with here. Namely, what we do is this: we rewrite equation star in this form. Namely, we can rewrite it as q hat minus lambda times the identity operator acting on psi is equal to the zero vector. Okay, this is the same as equation star. I just moved what was on the right-hand side to the left-hand side. And now we can rewrite this. We can say, rewrite this as, how can we rewrite this? We can rewrite this as the operator q hat minus the lambda times the identity is an operator that is not invertible. You see how that's the same? Here, up here, we have psi is an eigenvector and lambda is the eigenvalue. Now we have here that q hat minus lambda acting on psi is 0. But this means, this equation here, this one, it means that all multiples of psi, all Hilbert space vectors that are multiples of psi, get mapped onto the 0 vector by q hat minus lambda. Which means that q hat minus lambda cannot possibly be inverted, because how would you in the inverse know what multiple of psi you were dealing with, for example? So therefore, what we have is that q hat minus lambda times the identity operator is not an invertible operator. But the amazing thing here is that this statement does not refer to eigenvectors. This is a statement only about eigenvalues. Only lambda occurs in here. We got rid of the psi in this. So this suggests that what we should work with is this condition here in the Hilbert space framework in infinite dimensions in order to stay safe and have everything well defined. This is what we should work with. We should ask, when is the operator q hat minus lambda invertible and when is it not? That should tell us something about eigenvectors, eigenvalues, without having to worry, at least not initially, about eigenvectors and their existence in the Hilbert space. Now we are ready to define the spectrum. And the spectrum will intuitively consist of all eigenvalues, which have eigenvectors, but also of all those eigenvalues that do not have vectors in the Hilbert space. They are kind of eigenvalues, but they're not in the eigenvectors are not in Hilbert space. This way, with the condition in the box, we can catch them. All right, so here's the definition. definition. The spectrum of an operator Q hat is the set of all numbers lambda in the complex plane for which the operator Q hat minus lambda the identity space does not possess an inverse Q hat minus lambda 1 on all of the Hilbert space H. Okay. What I need to add to this is that this here, the inverse of Q hat minus lambda, if it exists, has a name. It is called the resolvent function of Q hat. Just a name, we won't really need it much in this course at all. All right, so I need to point out that this definition of the spectrum has a subtle extra point in here. What we are saying here is that a number lambda is in the spectrum of our operator Q hat if this operator Q hat minus lambda is not invertible in the sense that it's not invertible on all of the Hilbert space, which leads to special cases that we will need to consider apart. So we'll proceed here very carefully to make sure we are not missing something important. First of all, we notice that this definition includes all of the regular eigenvalues. So we notice here all eigenvalues of Q hat as defined previously. Let me show you where. As defined here. Lambda is an eigenvalue if we have an eigenvector in the Hilbert space such that Q hat psi is lambda psi, right? So that's an eigenvalue, the linear algebra type simplest case. All of these are, of course, in the spectrum of the operator by this definition, because for them, yeah, that just isn't an inverse of Q hat minus lambda 1. Right? It just cannot be an inverse because many Hilbert space vectors are all mapped into 0. And all multiples of the eigenvector get mapped into 0. So clearly that cannot be invertible, and therefore that's that. So we notice that all eigenvalues of Q hat, as defined previously, are in the spectrum, spec of Q, right? As defined here. Now, we adopt a definition, namely, we say that the set of eigenvalues, of Q hat forms the so-called point spectrum, of Q hat. Now, why would one adopt that name? It's because one can prove, but it would take us too far here, one can prove that the eigenvalues of an operator occur separated. They occur in an isolated way. They don't occur in a continuum. So we call them, we say that they belong to the so-called point spectrum of the operators, of the operator in question. Now, are there any other lambda in the spectrum of our operator? Are there any other lambda in the spectrum of Q? Well, that depends obviously on the operator Q, but how could it happen? Yes, there can be. There can be other. And how that can happen is that we observe how that can happen. If the inverse of Q hat minus lambda 1 exists, then lambda can still be in the spectrum. Let me remind you how that happens. See, the spectrum is defined as the set of all those values lambda such that this thing doesn't have an inverse on the Hilbert space. So either it has no inverse, and we just covered that case, or it has an inverse, but it's not defined on the entire Hilbert space. This is the escape possibility, but it's the interesting one, the one that allows us to cover the continuous spectrum case, the case of non-normalizable eigenvectors, right? So now we're looking at the case where lambda is an element of the spectrum, not because there is no inverse. No, there is an inverse, but it's just not defined on the entire Hilbert space. So we observe that if that inverse exists, but the domain of Q hat minus lambda, the identity inverse, is not equal to the Hilbert space, then lambda is also in the spectrum. i.e., lambda is an element of spec of Q. And there are two possibilities now. Two possibilities for exactly how this can happen. Possibilities. A, we could have that the domain of Q hat minus lambda the identity inverse. So the inverse exists, and it is smaller than the Hilbert space. The domain is smaller than the Hilbert space, but it is dense in the Hilbert space. Is dense in H. Meaning there exists no vector phi in H which would have the property that phi is orthogonal to the entire domain of Q hat minus lambda, the identity inverse. And obviously the only remaining other possibility is that B, the domain of the operator Q hat minus lambda, the identity inverse, is not dense in the Hilbert space. This means it's a really defective inverse, because it's not only not acting on the entire Hilbert space, but the domain is actually orthogonal to part of the Hilbert space. Now, I need to move this a little bit. The case A, where the inverse exists but is not in the is not the entire Hilbert space. This case is the interesting case. We then say that lambda is in the continuous spectrum, or continuous part of the spectrum, well, just continuous spectrum of Q hat. This is the situation for the position operators and the momentum operators of quantum mechanics. So this will be occurring quite frequently. The other case, the case B down here, is something that we don't need to worry much about. We then say, if this happens, we then say that lambda is in the residual spectrum of Q hat. Now, it turns out that for self-adjoint and unitary operators, there is no residual spectrum, and that's great, so we can disregard this. So this occurs rarely. Case B occurs rarely and never for unitary and for self-adjoined operators. All right. So what this means is that we usually are only dealing with the point spectrum of an operator and the continuous spectrum of an operator. And we need a name now for these vectors for these numbers in the spectrum that are not part of the point spectrum. Because remember that the elements of the point spectrum were just the traditional eigenvalues. They have eigenvectors in the Hilbert space. But how shall we call the numbers in the spectrum that do not have normalizable eigenvectors? The numbers that belong to the continuous spectrum. And the definition here is this. Definition. the elements of the continuous spectrum of Q hat are called approximate eigenvalues of Q hat. Why would that be a good name? Approximate eigenvalues. Why? Well, there is a theorem that can be proven about them, which is super useful to know. Proposition of great physical significance. If lambda is an approximate eigenvalue of Q hat, then it means that even though there is no eigenvector for lambda, so there's no vector in the Hilbert space for which lambda would be an eigenvalue, you can write down vectors that get arbitrarily close to being an eigenvector lambda. So we can approximate with arbitrary accuracy eigenvectors to lambda. Then we have that for all epsilon larger 0, there exists a state psi in the domain of our operator Q hat, which is normalized with the length of the vector psi being 1, so that Q hat minus lambda, the identity, is having norm, which is, sorry, this has to act on psi. This acting on psi is a vector whose length is smaller than epsilon. You see, if epsilon is 10 to the minus 1 million, then this means that Q hat minus lambda 1 applied to psi is a vector that's extremely short. It's basically the 0 vector, which would mean that we have an eigenvector to Q hat. So we can get arbitrarily close, and yet the eigenvector itself does not exist, right? But we can get arbitrarily close. That's very important. It means that yes, the eigenvectors are not in the Hilbert space, but you can write down Hilbert space vectors that get arbitrarily close to being eigenvectors. So this means that there are vectors psi that get arbitrarily close to being an eigenvector of Q hat with eigenvalue lambda. You may wonder, have I ever seen anything like that before? You probably have. A related example is this one. Remember delta function of x minus x naught? It looks like x, and then you have delta of x minus x naught. It looks how? If this is x naught, then this is a function that's 0 everywhere, except here it spikes, right? Not quite like that. It spikes anyway. And this is sometimes in first courses of quantum mechanics introduced as a position eigenvector wave function. And of course, this thing is not normalizable. You can't integrate over the square of the Dirac delta function. It's just not defined. You can integrate over Dirac delta, but in order to normalize this, you would have to square it, right? You have to take the vector and square it in order to get the norm of it. Can't do this. But delta of x minus x naught can be approximated arbitrarily well, by the function epsilon divided by pi 1 over x minus x naught squared plus epsilon squared. This is approximately delta of x minus x naught. If you let epsilon go to 0, this becomes arbitrarily close to the Dirac delta. But this thing here is square integrable. It's normalizable because it decays like 1 over x squared. This thing is normalizable, that thing is not. This is, in a concrete representation, as we will later see, this is an instance of having a non-normalizable eigenvector that can be approximated to arbitrary accuracy by actual eigenvectors, by actual vectors in the Hilbert space. All right, so now we are basically ready for the spectral theorem. We are now ready for the spectral theorem. Theorem for self-adjoint operators. And what it says is that self-adjoint operators always have a spectrum that's real, and that consists of a point spectrum and or a continuous spectrum mixture, and mixtures of that, and that there are correspondingly also approximate, that there are eigenvectors and approximate eigenvectors, and together they form what is effectively a basis. Not exactly a Hilbert basis, but a basis, or a spectral decomposition, more accurately, of the Hilbert space vectors and Hilbert space operators. So we will proceed with this next time. Okay, see you then. See you on Wednesday.